Sorry, just getting the laptop set up. I apologize for that, but we're gonna, let me just go ahead and share my screen. Oh, hold up, let me make sure I'm on the right Wi-Fi.
Yeah, because, you know, we can't replace them. No, we talk about how sharks. Polymers. We talk about how sharks can't get cancer, you know?
That's awesome.
That is awesome.
That's why
That's
they
really
live,
cool.
live forever. Can you imagine living in polluted water and never getting sick?
Wow.
Man, crazy.
But also, like, I hate how, like, the birth process for sharks. They literally eat their siblings in the water.
They
Well, like, we do too, but it's like, they kind of absorb, eat it.
Yeah, we absorb. We kind of just.
Yeah, well, like, let's be together. Oops.
All right. Let me share my screen right quick and we'll get started. Again, my apologies for being a little bit late. Friday, we don't have class, by the way, because all classes are canceled after 10. After 10 o'clock.
Oh, really? That's not that bad. Creating me. Yeah. No, but see, they switched their teacher. That made me so mad. Without telling us.
But that's because there's a teacher shortage.
I don't care. I want to tell
In the math department?
Yeah, we got a teacher shortage.
them. You can come join the math department. You're a good teacher.
I could probably teach like algebra 1, algebra 2. I could probably teach Cal 1.
That counts too. Cool.
I can't teach Cal 2. I love Cal 2. I can't teach it. I know my limits, but I do love it.
We could learn together.
That was the hardest class, math class I took in college. Yeah, that great teacher.
This was hard.
Makes all the difference. Yeah, it was very difficult.
Our theory in Cooper tried this over.
Well, guess what I did was I taught myself how to integrate my parts. Because that was the hardest part for me, integrate my parts. So we got snowed in the last day of school. And I was stuck in my room, took my book out. Homecoming week. I'm kind of glad we don't have class Friday because I'll be here by myself. Anyway.
It's November.
All right. I'm gonna put out this. All right, we're going back to, I think the last thing we covered was the E2 elimination. Is that right?
We did alpine stability. We're talking about
Yeah,
that.
talk about that alpine stability.
Hyper conjugation.
Yep, and how all of that ties into the E2 reaction and the zinc cell fusion. That's the reason we covered all that is because this is the justification for, or the explanation for why eliminations follow zinc cell fusion. All right, let's do the E1 and then we're gonna work through a few problems. I'm gonna let y'all go a little early. Because I need to catch up. I was out of town yesterday. Yeah. Let me grab the E1 example. So elimination can happen apart from a base in the case of the E1. Okay, so before we even start with E1, and I'll start talking about all this stuff. Somebody tell me what the 1 means in E1. The E is for elimination. But what's the, it's unimolecular. So for E1, I like to establish that up front. For E1, it's unimolecular, just like SN1. So what would, is that big enough? What would the rate law be for E1 elimination? If the 1 is unimolecular.
Equals subs times.
Okay, so it's elimination, so there's no nuclear problem. But the rate is equal to K times the concentration of what? Substrate.
Great.
K times concentration of soil, just like SM1. So the same things that facilitate SM1 also facilitate SN2, like protein solvents, good leaving groups. In this case, it's also going to follow Zaitsel's rule as well. So let's just draw the product first. Then we're going to show how it happened. And then from there, we'll talk about the other elements of the reaction, like the energy diagram and the transition state, so on and so forth. Actually, with the E1, what do you think about the rate determining step is going to be? Because it follows the exact same pathway as SM1. So what will be the rate determining step? What was the rate determining step for SM1? The slow step. What step determined the rate? Was it the substitution part? Was it the loss of the leaving group? So for SM1 and E1, the rate determining step is the loss of the leaving group. Right, for SM1, you had a leaving group that left first, right? And left the carbocation behind. All right, that's the slow step. Here it's going to be the same thing, but here is the, let me just show the product. And we'll come back and talk about how it happened. All right, so that's my elimination product plus water plus sulfuric acid. It's not a reactant. It's actually going to serve as a type of catalyst. It will be like a catalyst. It's going to facilitate the reaction, but it's not going to get consumed. All right. So with the E1, we're going to go through this particular reaction using sulfuric acid and to show how that works, how the elimination works. So here, I'm just going to rewrite it for actually the copy. It's going to be this alcohol plus H2 SO4. So this is the structure of sulfuric acid. All right. The first step in this particular reaction is not the loss of the leaving group because OH is a very bad leaving group. So you got to make it better. That's the purpose of the sulfuric acid. Four leaving groups. So anytime you want to eliminate or substitute using the hydroxyl group, you want to substitute that, you have to actually make it a better leaving group first. Here's a good question. See if you've been paying attention. How do we determine the quality of a leaving group? What can we use to make that determination? Or any leaving group?
Its pKa value.
Say that again.
Its pKa value.
Or is it the leaving group's pKa value or the conjugate acid of the leaving group?
The conjugate acid.
So the pKa of the conjugate acid will tell us whether the leaving group is good or bad. If you have that chart available, since you answered that, if you don't mind, tell me what the pKa of the conjugate acid of the OH group is, which is water, by the way. What's the pKa of water?
Negative 1.7.
I think you're looking at H3O plus. Water should be somewhere about 16 or 17. Is that right? The 16?
Yeah, that's right.
All right. So the pKa of so anytime OH is a leaving group, you're gonna have to do something to make it a better leaving group. All right, so the first step in this reaction is going to be proton transfer. Or to the hydroxyl group, right? And that's gonna make an intermediate. Here. Water is a much better leaving group than OH. So this is an intermediate, and we call this a hydronium ion. Right, so that plus conjugate base of sulfuric acid. Right, so that's the conjugate base of that. Because once you do the proton transfer, you're going to get the conjugate base of that acid. All right, so we get to the hydronium ion. What's next? Once I get here, if it's following the same path as SM1. Anybody? Once I get to that hydronium ion, what do you think happens next? Well, the elimination is last, but before you eliminate, if it's unimolecular, and this is the elimination substrate, the fact that it follows the SM1 pathway, we're going to lose that leaving. And then get to solid. All right. Any questions about that? So we had to make OH a better leaving group, and we added a proton to it that I would usually do it. We lost water, and we made a carbocation intermediate. And now we need to eliminate. The proton transfer first. Lost leaving group. Lost our leaving group. That's the slow, that's the rate determinant step. For E1 and SM1 is the loss of leaving group. That's what controls the rate of reaction. And then here is the elimination step. When we did E2, what do we look for in order to be able to eliminate? There's a reason why I highlighted the hydrogens next door to the plus charge. What do we call those hydrogens in, what did we call them in the E2? alpha protons. Those are the protons that get eliminated, that get pulled off in elimination. Right? In this step, you got two choices for your base because you still need a base, you just don't need an external base. So the water can act as a base and do the elimination, or the conjugate base of sulfuric acid can act as a base. Which one do you want to use? It really doesn't matter, but they both are capable of acting as a base. Okay. Sulfuric acid? Yeah, sure, let's do that. So we can take that, and let me write that up here. Conjugate base of H2SO4 or water. Right. So for that elimination step, it can be the conjugate base of H2SO4 or water. Either one, but we're going to use the conjugate base of sulfuric acid. Cheap. All right. So let's take that, bring it in, and it's just going to simply do a proton transfer. I'm going to draw a arrow from here to here. Then I'm going to show H bond becoming a pi bond like so. Just like we did with the E2. That part, the proton transfer to make the double bond is the same as the E2. All right, questions about that part? This is your elimination product here. And that hydrogen, one of those hydrogens is still left, so don't panic about that part. And we got two hydrogens still over here. Those two don't get touched. That's going to be that plus water plus but the sulfuric acid never gets used up. Right? It always gets regenerated. All right. Any questions about the mechanism? Any questions about the reaction? So if this follows a similar path to the SM1, is it concerted or stepwise?
Stepwise.
Stepwise, good. It's a stepwise reaction. What does that mean for the energy diagram? How many steps? Right, we had the proton transfer step. Is that right? Then we had, good, we had the proton transfer, we had the loss of the leaving group, and then we had the elimination step. So those two steps. Right, so the first step, the proton transfer, is usually rapid, exothermic, right, that gets us to this intermediate reaction. We'll call it intermediate 1. And then when you lose water from that intermediate to get to your chromocation, that's the rate determining step. So what does that mean in terms of activation energy? Compared to all the other steps? If the loss of water or the loss of leaving group is rate determining, what does that mean for the activation energy of that step relative to all your other steps? Is it higher or lower? Think about it for a second. If it's slow, then that means the activation energy should be higher than the other step, right? So when we show that, we don't know it quantitatively. But we gotta measure, we can show it like so, right? With a higher activation energy in the first step. And that's going to get me intermediate 2, which is the carbocation. And then the final step is the elimination. So reactant, we got 2 intermediates, and then product. And we know the rate law is based on this step right here. That's my rate determinant step, that's second step. All right, what does the transition state look like for that step? The loss of water. The loss of my leaving group. Help me out. What did it look like for the SM1 when the leaving group got lost? Is that right? Partially broken bond between carbon and oxygen. Just like the SM1. Right? So we're not gonna go into all the same level of detail with the E1 like we did with the SM1 because they follow the same principles. All right, any questions? I have another question. How many transition states does this reaction go through in total? Say 3?
Yeah.
Every step has a transition state, and there are only 3 steps, right? So that's 1, and that's 1 also. All right. Any questions about the E1 mechanism, energy diagram, transition state, anything? Arrows. All right, let me pull up a couple of examples to work through. For 834, let's do C, and let's do 841. Let's do All right, so here's my substrate that I'm reacting this with OH minus. OH minus doesn't really exist like it by itself, but you'll always have a counter ion. Sodium, potassium, lithium, some metal. Typically group 1 or group 2 metal. So this is, it's telling us in the instructions that it's E2. What does that mean? We know, we see the base, but OH is the base. It's the substrate. What am I looking for? Oh, and this is my leading. You can't see it. Oh, yes, you can. No, it's my leading. Once I find my leaving group, what am I looking for next? In the what's the next part of that strategy? Find a leaving group, and then what else?
Alpha protons.
Good. Find the alpha proton, and this is going to be whatever carbons are adjacent to that carbon. Right. So here, here, and here. Right. So this is the carbon that contains the leaving group. Right here. So everything adjacent to it is alpha. That's alpha, and so it is. So how many products are we going to get?
Three.
3 products. Excellent. Right? How can we predict those products? I gave you a strategy the other day. What can you do in the substrate, even without going through all the arrows? What can you do in the substrate to predict the product? Let me put the hydrogen in, by the way.
Excuse me, I have a question.
Go ahead.
Are there 3 products because there are 3 alpha hydrogens, or?
Hold on, say that one more time.
I just want to know, like, can you say again, like, why there are 3 products?
Yeah, because we have 3 alpha sites that are going to get eliminated. Everywhere I have that little lowercase Greek a for alpha, I can pull off a hydrogen and put a double bond there
Okay.
and kick out the leaving group. Right? Let's go through the arrows for the first 2 products. Let me draw those. Let's take this one first. So that alpha proton, if I bring in OH minus, pull it off. Right, that's how it happens. Is that right? It's all conservative. I'll pull off that proton. I use the electrons to make my pi bond. The pi bond is always going to be between the alpha carbon and the carbon with a leaving group. Always, regardless of what side that alpha carbon is on. Right, so that's my first product. It looks kind of crappy. Right? Anybody not see that? So on this alpha side right here, gonna be a double bond right there. Between those two carbons. If I pull off that alpha proton that's on the left side. All right, let's do the other side. I'm gonna just copy this. For the sake of time. All right, we do this side. Right. Same thing is gonna happen, right? I'll give you time to write it out because I copied it, so I kind of cheated. Well, I think Chase cheated. Not the same. So we're gonna do this right here. This pair of electrons is gonna come here. And pick up my leaving. So now the double bond is gonna be here. So we know it's two. Is that right? So here's what my double bond is now. Any questions about those two? Almost out of time. I thought we'd get to an E1, but. All right, let's do the last one.
Is the leaving group is that still in the? Are we drawing those in the product or not for the individual like reactions?
Say that one more time. You said there's a leaving group.
Are we still drawing the leaving group in the little individual reactions like all three of them?
Product.
Yeah.
Yeah, we can show that. That's not a problem. It's going to be the same for all three. So it's going to be plus water plus I minus. It'll be the same for all of them. All three reactions are going to give you the same side product. That's a good question. And it's always good to keep track of your atoms and side products and everything. So that's a great question. All right, what about the last one? Right here. Is where the reaction is going to take place. So there's going to be a double bond between these two carbons. That's coming there, coming here, and we're picking out. All right, you draw that product. If you want, you can annotate the screen also. If somebody who's on here, who's logged in, wants to draw the product, you can just annotate the screen. Or you can tell me what the product is going to look like. CH2. Don't second guess that. You see the hydrogen coming out, right? Yeah, so it'll be a CH2. Don't second guess it, man. It'll be right here. Is that it? All right. Which one do you think is major according to Zatev's rule? How do we determine which product is major? What are we looking for? which double bond or which alkene is more substitute. Is that right? So up top, if we look at the double bond that's highlighted, it has 1, 2, 3, 4 carbons attached. Look at the next one, it has 1, 2, 3 carbons attached. Look at the next one, it has 2 carbons attached. So which one is major? Or more, which one is more substitute? First one. What do we call it? It has 4 things attached to it. Tetra substitute. And it's measured based on the Zell rule. All right. Any questions about that? I'm gonna stop here. I'm not gonna push it. We only got a minute left anyway. Any questions about that? All right, remember, for those who are logged in, in case you came in after I said it, no class on Friday. All right. Excuse me. We should be coming up too on the next exam. Maybe next week we'll take it. That way it won't be overloaded with material. And that'll be 4 exams, and we'll still have time to take a 5th one before we take the final. More tests you take, more chances you have of getting a better grade. So we're gonna stop here and we'll pick up on Monday.
I have a question about the E1 reaction.
Yeah, go ahead.
So like how, wait, is this, so the reaction we did, was that E1?
Just now?
Yeah,
No, E2.
no, E2, okay, all right. So do E1 reactions have different products as well, or